Now students, I am going to explain you the laws of refraction or laws of reflection or the activity which is given in our textbook. The same activity we are going to do here in this video. Okay. So students, laws of reflection is nothing but, see here, angle of incidence is always equal to angle of reflection. So this experiment is like this. We are taking a horizontal paper and we have placed a white paper on it. Now we have, with the help of comb, we have taken in such a way that the light ray which is been created travels in a straight line. Okay, you can take a paper or opaque object with a single hole so that the light is incident is on a singular track. Okay, the straight line, you can see it in the video. Here the light is incidented and after hitting the mirror it gets reflected. Okay, now when you imagine a normal at the point of contact, both the angles are same. So at different positions we place the incident light and different angles, and so we get different angles of reflection. So for different angles of incidence we get equal different values of reflection. Here what we wanted to explain you, or what we want to try to show you is, here angle of incidence is 30 degrees and angle of reflection is also 29.9, that is approximately equal to angle of reflection. So this is a lab activity. Now I am going to give you the videos of the same laws of reflection related to different collections or activity list, experiment list. Watch them and you can write the answer in your own words. Anyhow, we are in the next video I am going to cover the entire video is been dedicated for this particular lab activity which is there in our textbook.
In our previous video, we discussed the two laws of reflection. Today, we will do one cool experiment that you can do at your home to verify the laws. Cover a table with a white sheet of paper. Take a comb and cover all its openings except the middle one. You can use black paper to cover them. Place the comb perpendicular to the white sheet of paper as shown. Now light up a torch. Throw its light through the opening of the comb from one side. Adjust the torch in such a way that you should be able to see the light on the white sheet of paper. Next, we place the plane surface of the mirror in the path of this light. What did you see? Did the light get reflected? Yes, you can clearly see the reflection of light on the sheet of paper. Represent this light with the incident ray and reflected ray drawn on this white sheet of paper like this. Also draw a normal to the mirror surface. Remember, normal is a perpendicular line drawn at the point of incidence. What are these two angles called? This angle is called angle of incidence and represented by I, while this angle is called angle of reflection represented by R. Measure these two angles with the help of a protractor. The measure of the two angles will almost be the same. They are approximately equal. This is the first law of reflection. So with this experiment, you can verify this law. Well, if you're still not convinced, you can take further readings by changing the direction of the incident light. Change this angle of incidence by moving the comb slightly. Make sure that the point of incidence is the same in both cases. That is, this point here is same as it was previously. But notice that this time the angle of incidence is greater than the previous one. So by the first law of reflection of light, the angle of reflection should also be greater. And that is the case indeed. Measure both the angles and again you will find that they are approximately equal. Take 2 more readings to complete this table. Do you notice anything strange here? The first law tells us that angle of incidence is equal to angle of reflection and not approximately equal. Why am I using the word approximately? Well, there are chances of errors that may come about during measurements of things. We can refer to them as human errors. It also depends on narrowness of the light beam. Narrower this beam, more accurate will be the results. And this is the reason why we are passing a light through the small opening of the comb. Only a narrow beam of light from the torch passes through the small slit. This minimizes the error in the measurement. Also, one more thing that we need to keep in mind is that the beam of light is different from the ray of light. For example, in this experiment, the light you see is a beam of light. A ray of light is simply an idealization of a beam. We can see a beam, but we cannot see a ray of light. However, at this stage, we can think of ray of light as a narrow beam of light. And we will call this narrow beam a ray of light.
Hello scientific audience, how are you all? So today I am going to demonstrate the laws of reflection of light by using a laser, protractor, some basic stationery, plane mirror and the screen. So screen is nothing but a white background. So I had a small piece of cardboard on which, a small box on which I have attached a white A4 size paper. So this is going to act as our screen. Now what happens is, this is the mirror and the first law states that incident ray, reflected ray and normal, they all lie on the same plane. So that can be easily demonstrated even without the use of the protractor. And you will understand why we are using protractor, because the second law states that the angle of incidence and the angle of reflection are same. So we need to prove that. So here I am going to use a red laser, right, in order to support my demonstration. And anything which you see in the mirror will be the reflection. We are supposed to concentrate on this white screen. Okay, so this is our incident ray. The incident ray is this one, which is seen over here, and you will see that the reflected ray will also be on this particular white screen. So this white screen is nothing but, you can consider this as y-axis, this as x-axis, and this will be z-axis towards us. So this white screen is nothing but xy plane, and the incident ray and the reflected ray would definitely be on the xy plane. And from here, if you draw the normal that separates both incident and reflected ray, you will see that all three will on the same plane here. So I'm shining the red laser from this side, and you can clearly see the incident ray and the reflected ray as well. So incident ray, this is the incident ray, that is the reflected ray, and the normal is here. And you can see that all three lie on the same plane. To have a better view, I have switched off the light in the room, and now this is very well visible that this is our incident ray, that is our reflected ray, and here is our normal. And this point where the laser light would strike on the mirror, that would be the point of incidence, right? Now unfortunately I doesn't have another stand so that I can hold this laser, so I am doing it by my hand. So the point of incidence may keep on changing, but hopefully the idea is you have understood. Okay, so we are good to go for the second law of reflection, that is angle of incidence is equal to the angle of reflection. And what I have done is the same cardboard box on which I had fixed this A4 size paper, and now I have also fixed a protractor on this white A4 size paper so it doesn't move with the help of a glue, right? Okay, now what my plan is that this is my plane mirror, and this plane mirror I am going to arrange perpendicular to this plane of paper, correct? So I'm going to put it somewhere here on the protractor, and I would make sure that this plane mirror is perpendicular to the plane of paper and along this line, right? Like this. And now I would make sure that this mirror does not move, so I will hold this mirror rigidly. Now I will pass the incident ray through here, so it would strike the mirror and it will go somewhere like this. So this would be my target point. I am planning to incident the light at this point, exactly at the middle point over here. So that would become the point of incidence, and this would be the direction of my incident ray. So incident ray would pass from here, it would strike and it would go like this, right? And I would be passing through this 30 degree, right? So in this particular case, this is our point of incidence. So this is our incident ray, that is our point of incidence, and perpendicular to the mirror there is always a normal. So this is normal, so that is 30 degree, and the normal will always pass through 90 degree because from here the perpendicular line passes through 90 degree. So this is our normal. So this angle is 60 degree. So I'm making sure that the angle of incidence is 60 degree because this is 30 degree, this is 90 degree. So the angle of incidence is 60 degree. So if I am passing a ray of light through 30 degree, I should get the ray of light from the other end also as 30 degree, right? So let us do that. Through this laser light again, I will pass the incident ray through 30 degree. So this is my incident ray. It is going to strike at the point, and after reflection, as you can see, it passes through the 30 degree only from the other side. This is 30 degree and this is the same point, and look, this is the reflected ray that is on the same 30 degree on the other side. You can see here this is 30 degree, so your attention should be over here, correct? Have a look at it once again. I am passing the incident ray from 30 degree. It strikes exactly at the point that we decided, and there you see it passes from the 30 degree mark only. So that means the reflected ray is on the other side of the normal, and the angle of incidence and angle of reflection are the same. So hopefully guys, you have understood this demonstration.
In this lesson, we're going to use a light box to have a look at the law of reflection. The light box shines light out of both sides, but we're going to use the side that produces nice, clean, straight beams. The kit comes with a quadruple ray forming plate, a triple ray forming plate, a fat single ray forming plate, or a thin single ray forming plate, which is the one we'll be using in this prac. The other side of the light box that has the mirrors is useful for studying color. You can mix, for example, red light with blue light or green light with red light, but we're not going to use the mirror side in this lesson. The aim of this practical exercise is to find out how a light beam's angle of incidence compares with its angle of reflection. To do this, we need to accurately record the path of the light rays and then use a protractor to measure the angles. The instructions are all on the law of reflection prac sheet, but I'll show you what to do right now. Firstly, draw a line on a piece of paper and then place the back surface of the mirror on the line, since most of the light reflects from the back surface. You can see when we get a close-up that the mirror's back surface is on the line, while the glass is in front of the line. Direct the light ray at an angle towards the mirror and mark the path of the incident and reflected rays by placing 2 small dots on each of them. Using a ruler, connect the dots with straight lines. You can now measure the angle of incidence and the angle of reflection with a protractor, which is best placed like this. The line marked 90 degrees on the protractor will be your 0 degrees, so in this case, the angle of reflection is 35 degrees, and the angle of incidence is also 35 degrees. So, just repeating, when using a protractor in this situation, you have to ignore the degrees marked on it and measure the angle of each light ray with respect to the normal. The angle of incidence in this case is 10, 20, 30, 35 degrees, and the angle of reflection is 10, 20, 30, 35 degrees as well. Once you've measured the angles, you can draw in the normal line and mark in the angles and the direction that the light was travelling in. Do a total of 4 so-called ray tracings, making sure that you vary the incident angle each time, fill in the table, and answer the questions.
The light travels in a straight line. Just as a ball bounces off a wall when we hit it, similarly, the light bounces off objects when it strikes it. The most important fact is that the angle at which the light strikes an object is same as the angle at which it gets reflected. Let us study about it in detail. The reflection of light at a surface obeys the following 2 laws, which are called the laws of reflection. According to this law, angle of incidence is always equal to the angle of reflection. That is, angle I is equal to angle R. The incident ray, the normal at the point of incidence, and the reflected ray all lie in the same plane.
Get Doubtbox on a device of your choice. We have education tablet, pen drive for PCs, SD card, smart TV apps, and online versions available. Register today for a free trial and experience the new way of learning.
Our topic for today is laws of reflection.
Good job.
What happened to our light?
No idea.
I have an idea.
Really?
Huh?
Consider this ray of light which strikes a mirror. This ray of light is called the incident ray. The point at which the incident ray strikes the mirror is called the point of incidence.
Let's go up.
Draw a line perpendicular to the mirror through the point of incidence. This line is called normal. The angle which the incident ray makes with the normal is called the angle of incidence.
It's still not working.
My idea is not over yet.
When the incident ray strikes the mirror, it will bounce off the mirror. The ray which bounces off is called the reflected ray. The angle which the reflected ray makes with the normal is called angle of reflection. Let us learn the two laws of reflection. The angle of incidence is always equal to the angle of reflection. If the angle of incidence is 30 degrees, then the angle of reflection will also be 30 degrees. Remember that these angles are always measured from the normal, not from the mirror. The incident ray, the normal at the point of incidence, and the reflected ray all lie in the same plane.
In our previous video, we learnt that we see objects around us because of the light reflecting from them. Some objects like the sun, burning candle and the fluorescent bulb emit light of their own. They are also called luminous objects. Many objects around us are non-luminous, that is, they cannot generate their own light. However, these objects reflect the light from the luminous objects from their surfaces. And because of this reflection, we can see such objects. In which direction do the luminous objects emit their light? They emit light in all the possible directions. Consider a fluorescent bulb which is glowing. It is emitting light in all the directions. Let us denote each direction with a straight line and an arrow on it pointing in the direction where the light is traveling. So all these arrows represent various paths along which light is traveling. These arrows are what we call rays of light. Here's how we define a ray of light. A ray of light is a straight line path along which light travels. So now we know that light emitted by luminous objects travel in a variety of directions. Suppose rays of light from this fluorescent bulb fall on the surface. It being non-luminous reflects these rays, and these reflected rays travel along a certain path. Consider this plane surface. Suppose one of the rays of light from the bulb strikes at this point. This is called an incident ray. We know that this surface will reflect this ray, and the reflected ray will travel in this direction. Why only in this direction? Why not here or here? This is because rays of light obey certain laws of reflection when they strike any surface. Draw a perpendicular to the surface at the point of incidence. This line is also called normal. Here are the two laws of reflection that any light ray obeys. To understand the first one, we first need to know what angle of incidence and angle of reflection are. The angle of incidence is the angle made by the incident ray with the normal. It is denoted by I. The angle of reflection is the angle made by the reflected ray with the normal. It is denoted by R. So our first law says that the angle of incidence is always equal to the angle of reflection. I is equal to R. Here, as I is equal to R, if the incident ray strikes at this point, then the reflected ray will travel along this direction only so as to keep the measure of R same as I. If I move the incident ray here, then the reflected ray will also move to keep the measure of R same as I. I is always equal to R. Okay, so this was about the first statement. What about the second statement? The second one tells us that the incident ray, reflected ray and normal all lie in the same plane. So if I draw this scenario on the piece of paper, I will get this. Incident ray, reflected ray and the normal, all three are in the plane of the paper. The second law tells us that they will always be on the same plane. For example, if the reflected ray is in this direction instead of this, then the diagram will look like this. The incident ray and normal are in the plane of the paper, whereas the reflected ray is not in this plane. This violates our second law, and hence this ray will not be reflected in that direction. This is just not possible. It can only be like this. I will be equal to R, and they will lie on the same plane. I hope both the laws are clear now. In the next lesson, we will see an experiment based on this concept which you can easily perform at home. How do we see things around us? You will probably say it's the eyes that help us to see the objects around us. But will our eyes be able to see these objects in dark? No, we need light to see things. Without light, we cannot see the objects. But where is this light coming from? This light is coming from this source, which is a fluorescent bulb. You see that this bulb is emitting its own light. The objects which emit their own light are called luminous objects. Can you give me any other examples? Incandescent light bulb, the sun, the stars are also luminous objects. What about objects such as this table and chair? Do they emit their own light? No, these objects do not emit their own light. Such objects are called non-luminous. Almost everything around us is non-luminous. Objects made up of wood, plastic, cotton, metal are all non-luminous. What about the moon and the planets? They are also non-luminous. But if the moon is non-luminous, then how come we're able to see it at night? The answer to this is reflection of light. The reason we're able to see any non-luminous objects around us is because of the reflection of light. Reflection of light can simply be referred to as change in direction of light or bouncing of light from some surface. Just like the ball bounces from the ground, light reflects off from a smooth surface. Let me try to explain this in a simple way. The light from the source strikes the object and bounces off from its surface. And when this light reaches our eyes, we see that object. And this is how we see non-luminous objects. When the object is kept in front of the mirror, its image is formed in it. But will we be able to see the image in the dark? No, we won't. So the formation of the image is also due to reflection of light. Let this object be our human body, so at the same time we are looking at the image. First tell me, is our body a luminous or a non-luminous object? Well, it's non-luminous. Human body cannot emit its own light. So the light from the source is first incident on the human body. It gets reflected from it, and this reflected light strikes the mirror. This light is further reflected from the surface of the mirror and reaches our eyes. This is how we are able to see our image. Now, obviously, this is not the exact picture of the happenings. I just wanted to give you the intuitive feeling into how this happens. There are a lot of subtleties involved which we will learn in our higher grades. In our previous video, we discussed the two laws of reflection. Today, we will do one cool experiment that you can do at your home to verify the laws. Cover a table with a white sheet of paper. Take a comb and cover all its openings except the middle one. You can use black paper to cover them. Place the comb perpendicular to the white sheet of paper as shown. Now light up a torch. Throw its light through the opening of the comb from one side. Adjust the torch in such a way that you should be able to see the light on the white sheet of paper. Next, we place the plane surface of the mirror in the path of this light. What did you see? Did the light get reflected? Yes, you can clearly see the reflection of light on the sheet of paper. Represent this light with the incident ray and reflected ray drawn on this white sheet of paper like this. Also draw a normal to the mirror surface. Remember, normal is a perpendicular line drawn at the point of incidence. What are these two angles called? This angle is called angle of incidence and represented by I, while this angle is called angle of reflection represented by R. Measure these two angles with the help of a protractor. The measure of the two angles will almost be the same. They are approximately equal. This is the first law of reflection. So with this experiment, you can verify this law. Well, if you're still not convinced, you can take further readings by changing the direction of the incident light. Change this angle of incidence by moving the comb slightly. Make sure that the point of incidence is the same in both cases. That is, this point here is same as it was previously. But notice that this time the angle of incidence is greater than the previous one. So by the first law of reflection of light, the angle of reflection should also be greater. And that is the case indeed. Measure both the angles and again you will find that they are approximately equal. Take two more readings to complete this table. Do you notice anything strange here? The first law tells us that angle of incidence is equal to angle of reflection and not approximately equal. Why am I using the word approximately? Well, there are chances of errors that may come about during measurements of things. We can refer to them as human errors. It also depends on narrowness of the light beam. Narrower this beam, more accurate will be the results. And this is the reason why we are passing a light through the small opening of the comb. Only a narrow beam of light from the torch passes through the small slit. This minimizes the error in the measurement. Also, one more thing that we need to keep in mind is that the beam of light is different from the ray of light. For example, in this experiment, the light you see is a beam of light. A ray of light is simply an idealization of a beam. We can see a beam, but we cannot see a ray of light. However, at this stage, we can think of ray of light as a narrow beam of light. And we will call this narrow beam a ray of light.